So today I'm going to talk a little bit about hybrid batteries. We're going to get into this chapter these next 2 weeks, and we're going to talk a little bit about how the batteries are managed, and we're also going to talk about minor differences in the cells and things like that, and different monitoring criteria that we have for different chemistries. So one of the capabilities of hybrid vehicles today is that they're relatively safe to work on because we do various different things when the vehicle is shut off, regardless of fault conditions. So during normal operation, when you key off on a hybrid vehicle, we actually have a component or series of components, in this case, that is designed to disconnect the high voltage bus from the vehicle. So these components are called contactors, and I'm going to use my little makeshift pointer here, but these two components here, this guy and this guy, so both of these are high voltage contactors. You can view these basically like relays. So they have a pair of electrical terminals right down in here. I'll move some of this wiring out of the way. They have a pair of electrical contacts right down here. These are 12 volt contacts. These are 12 volt relays. And these relays are essentially what starts the vehicle. So when we key on the vehicle, in most hybrids, there's usually a short period where those relays are being checked for functionality. So you'll hear those make a series of clicks. And typically what that module is doing, so we have a battery module that's missing out of here, the management module. And what that module is doing is it's making a series of checks to make sure that we still have isolation before we put high voltage on this circuit. So we really want to make sure that when we do key on the vehicle, that before that ready light comes on the dash, before that ready light comes on, that module is doing some various checks to make sure that that high voltage DC bus is isolated from chassis ground. So it's going to turn on one relay first, check for isolation, then it's going to shut that relay off. It's going to turn the second relay on, check for isolation. And if that test passes, it will leave that relay on and turn that first relay back on. So we turn on, let's say positive, some varies on some vehicles, but we'll turn on positive, check for isolation, turn positive off, turn on negative, check for isolation. As long as we get isolation on the negative and we had a good test with the positive, we will go ahead and turn the positive back on. There's also a third component in this, and you can see it. The wiring for this component is right here. So this terminal would normally have our high voltage battery terminal going to it. And this terminal goes up here to a third device up in this corner. So I'm going to move you a little bit, just pivot you around. And this third device up in this corner, my camera skills, my tripod jujitsu. This third device up in here is a third relay or contactor. And this relay is used essentially to limit the current that is drawn from the battery when the main contactors come on. So what we have is a big battery back here that's capable of a lot of current. So all these cells would be at a relatively charged state. We have a big battery capable of a lot of current, and then at the other end of this high voltage bus we have capacitors that are going to take a lot of current to charge up very, very quickly depending on how discharged they are. So since those capacitors are normally discharged when the vehicle is turned on, we have to limit the current that happens when we first connect this battery to the bus. So as we do those checks, we're going to first turn on the positive relay or the positive contactor. We're going to check it. We're going to shut it off. We're going to turn on the negative contactor. We're going to check it, and then we're going to leave it on. And if that test passes, we're going to turn on this third contactor first. Okay, so we have positive on, positive off, negative on. Negative stays on provided that test passes. This relay takes the place of the positive relay and it runs in series with this resistor. Okay? That resistor limits the current that's capable of passing out of that battery to charge the capacitors, Once the capacitors in the high voltage bus come up to a certain voltage, this module receives a message from the inverter. It says capacitors are fully charged, go ahead and turn on the main contactor, and this main contactor comes back on. And again, the reason we do that is because of that inrush current when those capacitors are low in charge and the battery is being first applied to the circuit. Wanted to show you Ford's iteration of contactors. So right at the output of this battery, this is where the high voltage output comes out. We have all our cells right over here, so all in their nice little homes. This particular battery uses D-style cells. So, but if we come over here, the main contacts for this battery actually come out over here on this side and will be connected to this side. And then Ford has a contactor box. So we can't see all three, but there are 3 contactors inside this box, much like the Prius is. And then the output to those contactors sits right here, right down in that hole, those 2 screw terminals. So that's the output of the contactor box to the external outputs on the battery. So that's what Ford's contactor looks like. Again, with most manufacturers, the battery control module or the battery energy control module is right here. So it's inside the battery case. This battery actually has a little bit of active cooling in it as well. So these cooling ducts and fans over here pull in some cool air and blow it across the battery cells. It actually blows it in between the battery cells. And then one additional thing that's inside this one that is not in all of them is our battery charger. So this has a dedicated battery charger here. This battery also has some capabilities of high voltage jump start and things like that if we were to use that. So Ford puts a separate battery charger and actually does it right in here versus having a charging circuit in another piece of electronics like in the inverter. Honda's power electronics are a little bit different. So Honda's battery, the battery is actually normally in here. So that orange stick cell that I showed you with the Ford battery, that orange stick cell actually is a Honda cell. So those would all be in here. Honda's taken a different approach and put everything all in one spot. So this would be behind the rear seat on a Honda Civic Hybrid. These are our high voltage battery terminals coming over here to our main contactors. And also, believe it or not, these are our main capacitors. So they put the main capacitors inside the battery. One of the things I think they've done this for is just convenience and ease of use. Honda also has a couple different sensors and things like that that are present in this battery that are not present in others. But the entire inverter electronics, the capacitors, and the 3 motor outputs are all inside this battery case. So it's quite a bit of a different design versus other manufacturers where we're taking high voltage DC out of the battery and delivering it where we need. This takes high voltage DC and continues to keep it within this entire assembly. So we have a DC to DC converter in here for charging our 12 volt and running our 12 volt accessories. We have our power inverter that runs our motor. All of that is contained within this one unit. This does still have contactors to monitor for isolation and things like that. But again, just like the Ford, it is all one unit as opposed to separate units. This also has a serviceable drive electronics. So these drive electronics can be serviced by the technician. This one module comes out, and that's actually one of the few vehicles that does that sort of thing. So one thing I want you guys to notice about this battery, this is a fairly common arrangement and it's one of the easier arrangements to see, is each one of these modules has this stud terminal at each end. You can see this is the negative side, this is the positive side. Each of these modules is made up of 6 individual cells, much like a lead acid battery would be. And then each of those modules is paired up. So if we come down here, we can actually see that these terminals have copper bus bars that are going across every other module. So these are not connected here, but these are connected here. These copper bus bars do corrode. So if you notice these over here on this side, these are all very corroded. These are actually pretty corroded as well. You just can't tell because they're just darker. So they have that dark patina finish on them. That would indicate that those cells are probably pretty substantially discharged It's one of the reasons we can leave this battery open and we can fiddle around with it. But this is pretty significant corrosion. This would represent an issue on the vehicle that could cause concerns with lack of power or potentially setting trouble codes in the hybrid control unit or the battery control unit. What I want you to notice, and one of the nice parts about this particular battery model, is that we can open these cases up and you can see some of the wiring inside here in these. So these are all small gauge wires. These are not the current carrying wires for this battery. These wires are what's called sensing wires, and if you notice, they're attached to every other module in this battery. So every other module in this battery has a current carrying conductor, a sensing conductor attached to it. And all of those wires actually come over here to where the battery management module would be. So I'm going to take you up here a little bit. And this battery management module will actually watch and look at all of the individual block voltages. So Toyota calls it block voltages through this connector right here. So through this connector, we have connections to all of our different battery terminals, and we can watch those voltages across that battery. So we can understand whether or not we have a particular cell that's low on voltage or not charging correctly. We can understand whether or not there's a cell that's making additional heat rather than making power, because usually those cells are the ones that are going to be the weakest, and they're going to actually drag down the rest of the battery pack as opposed to continuing to power the vehicle. So this battery pack in particular is out of a early generation Prius. So this would be early second generation Prius. And you can see, once we have the case off, we can see that the high voltage safety plug, which would go right here, we're looking at the rearmost of the battery. So the rear seat would be out in front here, and this would be on the left side of the trunk. So once we remove that case, we can actually see what that high voltage safety disconnect does. So if we look in here, we have a couple of heavy gauge cables. These are about, I would say probably about 4 gauge cables. And these come to 2 of these battery modules. If you follow the sequence of the bus bars, so we have bus bars on these two, we have the 2 terminals for these wires here, and then again bus bars here, 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 and here. This high voltage disconnect actually chops this battery in half. So right about here, that high voltage disconnect is disconnecting between these 2 modules. So if we go bird's eye view and get up on top here, and you follow the way these bus bars work, if we go up top here and follow the way these bus bars work, we have a battery terminal connection for a wire here on the negative side, and if we follow through, goes through a bus bar, zigzags back to this side, back and forth, and this follows this pattern all the way down. When we get to this section here, I'll remove this cell for you. When we get to this section here, we have a bus bar here, goes up to this other side, another bus bar across that side, comes back down, and then we get to this terminal. So the current actually passes through these wires and through our high voltage disconnect, and then comes back up here to make it back to these remaining cells. Now Toyota did this so that if we had technicians repairing batteries and things like that, replacing modules and that sort of thing, which they did put DTC diagnostics for in their service information. If technicians were to go in and replace this battery, as long as that high voltage disconnect is out, we're not only disconnecting high voltage from the vehicle, but we're actually chopping this battery in half. So this battery, all told, is about 288 volts at its fully charged state. We can drop that voltage down significantly by just chopping off these last 2 cells. Each one of these modules is 7.2 volts. So we're going to chop off a bunch of that high voltage right here and minimize the danger to technicians that are working. One last concept that we'll talk about when we talk about batteries is the idea of balancing battery cells. So one of the things that the vehicle does on a regular basis is it actually balances these battery cells in a way that allows each cell to provide a similar amount of current and voltage to the high voltage bus. So that similar amount of voltage and current is crucial because if we had a cell that, say, was low resistance, that cell is going to be able to produce more power at lower resistance than the rest of the cells in the battery. The reason that's a good thing is if we had a high resistance cell, that cell is more likely to produce heat. When we're producing heat in a battery, we're not being as efficient as possible. So we're going to turn some of that battery's energy into heat. A lot of this comes down to the charge level. So these are nickel metal hydride chemistry cells, and a lot of that comes into charge level. In other words, what state of charge is individual cells at? If we have a cell that's on low charge, typically the resistance is going to be higher and it's going to be less capable of producing the amperage required to sustain voltage. So, for instance, failure analysis. If we had one cell in this pack that was, say, not having a good day, right? Low on state of charge, etc., so on and so forth. That one cell, because this battery is entirely wired in series, would drag down the output of the rest of the pack because that one cell would be creating heat, so it would be robbing energy from the rest of the cells. It would also be not contributing to the overall output voltage. So that is a problem for us. So in addition to monitoring the cell voltage, this hybrid module that's in the battery is also going to take a look at those voltages and determine if there's cells that are higher charged than other cells. So it does what's called balancing across this battery pack. So it will use a series of resistors that are keyed up with transistors inside the module, and as it is recharging this battery pack during regen and things like that, as it's recharging this battery pack, it's going to try to maintain all of these cells at a certain output voltage at all times. And that is really the key to making these batteries last longer. Nickel metal hydride cells are a little bit more difficult than lithium cells. Lithium cells, as long as they're properly managed and balanced, which they are balanced a little bit to more stringent standards than nickel metal hydride, but as long as they're properly balanced, lithium cells have a tendency to generate less heat in general and are less dependent on temperature and less dependent on state of charge level to produce the same given voltage. So they're balanced a little bit more stringently. However, they're also a little bit more reliable at staying in balance. So in addition to just monitoring these cells, these external wires are also for balancing operations. All right, I hope you enjoyed the video. It's just kind of a short video demonstrating some of the capabilities and internal circuitry in some of these batteries. Really, batteries are not that complicated. Typically, it is a lot of cells with very repeated circuitry. So as we saw the balancing plugs and things like that, that's all very repeated circuitry. So it may look a little bit daunting at first glance, but the majority of these batteries are actually pretty easy to remanufacture depending on what they are. Lithium packs have seen less remanufacturing capability than nickel metal hydride. Toyota built a lot of remanufacturing capability into these Prius batteries, but for the most part, all of them are serviceable in some way, shape, or form. Now, that does depend on the manufacturer. So the manufacturer may have technicians replacing cells in blocks versus individual cell modules like Toyota did. But for the most part, manufacturers like Nissan have taken part in modularized cell service where you can take out individual cell blocks and replace just those cell blocks. So it's not necessarily a case of having to replace the entire high voltage battery if you know what you're doing and if you are following the proper service procedures.